Hello and welcome to immutable, a show where there are always technical difficulties. Now it should be better. And today we actually have a very special episode of immutable because I'm not alone here. There is Tobi. Tobi is well, my video is mirrored, so let me do this. There is Tobi. Tobi is a postdoc, and he recently started working on performance of TigerBeetle. And in today's episode, we'll answer, or at least start to answer the question which bugs every one of you, and that is why TigerBeetle is slow. Why only 1 million transactions per second? Why can't it do like 10 million? Okay, and before we start, I'll let Tobi introduce himself because he can do this better than I am.
Yeah, so my name is Tobi. I'm a postdoctor at the Chair of Decentralized Information Systems and Data Management at Technical University of Munich. And I'm working a lot on distributed databases and in particular how to build the next generation OTP database for the cloud that is very cost efficient and very high performance. And since yesterday, I looked a bit into the performance of TigerBeetle. And now today I want to learn more about it. I'm also interested in the fact, why is it slow?
Uh, okay, so let's get started. And let me, okay, just a second. I want to also see Twitch chat. Can I actually pop it to new window? No, I can't. Okay. Yeah, anyway. Today, Tobi will be asking questions, but of course, I will try to follow anything asked in the chat. And again, the idea is that we'll just see this beautiful painting. No, let's not see this beautiful painting. We'll see like the hot path of a TigerBeetle. Which parts of a data plane, which parts actually take most of the time. And we'll start with like pictorial overview of what happens, and then we'll look at how this pictorial overview maps into the real code. Okay, so let's start with our time. Let's say that time goes left to right, and over time, TigerBeetle processes requests. And request in TigerBeetle is a financial transaction, a financial transfer. Transfer some amount of value from one account to another account. One key thing here is that TigerBeetle doesn't work with individual transfers. It always works with a batch of transfers. Batch of transfers 8k events. So in a single batch, we have 8k of transfers, and this batch is what goes through consensus, because we run a round of replication for 8k events. This actually means that replication is amortized across this entire batch and isn't actually the main cost center. Okay, now how the data evolves. These batches of requests are grouped. They are grouped in a so-called compaction interval. So let's maybe spread this out a little bit. Here are like actually some more of the requests, and this whole thing is 32 batches. So and then this picture is going to get repeated across the bars. So we have like this bar structure where every bar is 32 batches wide. In a single bar, we have 32 times 8 transfers, and because there are two accounts which are touched by a particular transfer, that is multiplied by 8, which is about 500,000 accounts. So that is, let me embiggen this a little bit, just a little bit. So this is the napkin math here. We have transfer, 8 key transfers is a batch, 32 batches is a bar, and a bar is 500,000 of accounts. Now, the next important fact is that within a bar, everything happens in memory. So while we are processing these individual transfers in a bar, we'll be accumulating the results into a hash table, a hash map of account balances, which maps account ID to balance. For details, account ID is U128, and balance is actually 4 balances, because we separately tracked credits and debits, and we separately track pending and posted amounts. But for now, kind of like just map account to balance, and this is in memory. Now, there is some impedance mismatch here, because for executing financial transfers, the data structure you want to have is a hash map, because to execute a transfer, you look up first balance by account ID, then you look up second balance by account ID, then you do arithmetic, and you update the balances. You need only point lookups. However, after this stuff goes through memory, it goes to disk. So here we'll have disk. And the data structure on disk is an LSM tree. And an LSM tree is not a hash data structure. It is a sorted data structure. So this is the major data transformation that occurs in the hot loop of TigerBeetle, where transfers arrive through the wire. They update in-memory hash map with accounts, because hash map is super fast for point lookups. And then this hash map is somehow transferred into an LSM tree. Tobi, do you know how LSM tree works, or should I explain that a little bit?
Yeah, so I know how that works.
Okay,
But
good.
you can still explain it.
I mean, there is like
Oh,
10 episodes about LSM3, so I will explain just a little bit. The core like component of an LSM tree is a so-called table, and table is very simple. Table, and this is just sorted array of n values stored on disk. And here we actually so yeah, table is sorted array of n values on disk. Now the LSM3 arranges multiple tables in a like sort of like like B-tree like data structure. Like, doesn't matter, which allows sorted lookups. One important thing here is that I kind of like just declared like a bunch of context here. Like there's like hash map, there is like 32, there is 8K, there is 500,000 accounts, and there is table. And now we could actually start tying this constant together. So I said that table on LSM3 is a table of n values. Now, what is n there? In TigerBeetle, we don't do dynamic memory allocation, so everything has to have an upper bounds. We don't allow our tables on disk to grow infinitely large. So the size of a table is exactly the size. Well, is there was some kind of laser pointer? Yeah, laser pointer. Yeah, the size of a table is exactly the sum total of all the events which happened during a single bar. So
the
after
transfer
we
is 128 bytes. Is that correct? Or how big is the transfer?
well, let's just see this. Let's go to TigerBeetle, and let's open TigerBeetle.zig, and let's open the transfer. And in the transfer, there should be time assert that the size of transfer is 128 bytes.
Hmm. So it's
So
roughly 60 megabyte, right? The in-memory table.
let's see. So let's see. Batch of transfers is 8K events, and it is also like 1 meg in size. I think if you divide 1 meg by 128 bytes, you should get something about 8 keys. So
Mm-hmm.
we get 32 megs of data, 32 batches in a single bar. So this is 32 megs of data. And that is like, means that like the size of the team is roughly 32 megs. But that's actually,
I think it's 64, right? Because of times 2.
yes, this is actually like more complicated because like our data model is transfers and accounts. And the thing we store in this hash map is like literally transfers and accounts. So the size of the the size of the transfers part of the hash map would be 32 megs. The size of the accounts would be slightly more because account. How large is an account? Well, no, account is also 128 megs, but there are for each transfer there are 2 accounts. So for accounts, that's going to be 64 megs. But when we convert data from hash map to an LSM tree, the relationship is not one-to-one. We actually create many different tables from account objects for indexes. So if you look at, let's look at the transfer. The trees for transfer we will have is that one will be the object tree. So this is LSM tree, which stores transfers sorted by their timestamps. So in that tree, the item is a transfer. And timestamp is an internal primary key of a TigerBeetle. The external key, which is specified by the user, is a transfer ID. Because timestamp is an internal ID, we also need some way to convert from this external large 128 IDs to internal small U64 IDs. And let me just improve my light here a little bit. Okay, so we need a way to map from this to this. The way we do this is that we store alongside the transfer object tree the so-called ID tree, which is an index. So ID tree stores pairs of IDs and timestamps sorted by IDs. So when you have an ID and you want to look up a corresponding timestamp, then you do a lookup in this ID tree, and then you get a timestamp, and then using this timestamp, you go and do lookup in the object tree, which is sorted by the timestamps. And similarly, we have indexes for some of the other fields. So, for example, TigerBeetle supports fetching all transfers which correspond to a particular account ID. And to do this, we store a tree which stores tuples of transfer timestamp and corresponding account timestamp. So if you want to sort it by the account timestamp. So if you want to look up all the transfers which belong to a particular account, you go into the tree, you find all tuples where the first component is the timestamp of the account, and that gives you a collection of transfer timestamps. And then using that collection of transfer timestamps, you look up the actual transfers in the object tree. So to make this picture more precise, we actually have separate tables here. Okay. And yes, the size of each individual table is determined by the amount of entries which could get into this table as a result of one bar of work. Okay, so is anything clear so far, or I'm completely obscure and confusing?
I'm good. I just wonder when the memory table is built from the hash map. Is it only at the end of the bar, or is it incrementally? Like after
Yes.
each batch, for instance, you move something from the hash table into the.
Yes. This is a great question, and this actually allows me to tell that what I was saying so far is kind of like a white lie. So let me zoom a little bit in here. And the thing is, while we are in the in-memory part of TigerBeetle, there is not only a hash map. There is also an array, which is called memory table. So when you process a transfer and it updates account balance, that update is reflected in this in-memory hash map and is also pushed onto this memory table array. Memory table array is not sorted. Rather, it is ordered just by insertion. And then when the time comes to move over to the next bar, what happens is that the memory table gets sorted into this still in memory, but already sorted table. And okay, let me maybe clarify this a little bit. So this thing is called table mutable because we are actually actively appending values to it. This thing, well, okay, so actually I describe this as a thing which is on disk, but at this point, at this level of detail, actually this table is called table immutable, and it is still in memory. So here I think I need to zoom out a bit and add one more bar to our picture and extend time retroactively. Okay, so in like the current bar, we accumulating data into in-memory hash table and in-memory array called table immutable. And at the end of this bar, this is our data in two places, in the hash table and in this unsorted array. Then when we flip between the bars, we sort this table mutable and get an in-memory table immutable, which is sorted array. It is like in the same shape that will be on the disk, sorted array, but it is still in memory. And in like the next bar will actually be, okay, let me change this to red because red is memory. So in the next bar, what will actually happen is that we'll start moving this immutable table to disk. So this is the evolution of data in TigerBeetle. Transfer arrives as a part of a batch. Its effects, the update to the corresponding account balances, are added into the hash table and in the table immutable. And they live there until the end of a bar. At the end of a bar, table immutable gets sorted into in-memory table immutable. Table mutable gets sorted into table immutable. And the objects live in this in-memory table for like during the next bar. And by the end of the next bar, they actually end up on disk in table immutable. So now let's get back to the transfer, which is right at the like start at the current time. So we got a new transfer. So this transfer talks about two accounts. How do we look up accounts? The first thing we do is that we look this account in the hash map. And if it is in the hash map, we say, okay, so this is the fresh state of the account. So it must be it. We've done. If it is not on the hash map, then we go and we try to look it up in the sorted array from the previous bar using binary search. So in the hash map, we look up it using a hash lookup. In the in-memory thing, we use binary search. And if it is not in memory, then we go and try to fetch it from disk using like LSM3 machinery. Okay, now like the obvious question here is like, why the hell we like duplicating data? Why we have like this hash map? Why not to go for sorted data structures everywhere? And the answer
I
is
have two questions quickly, if you have
yeah,
time.
sure.
So the hash map that will not be resetted, right? At the end of the bar, that basically lives forever. And you can evict things because you have not infinite space, but it's not really tied to these bar directly, right? Only the unsorted array, or is it really resetted or something?
I really love how you like anticipate exactly what I was going to talk about next. It is kind of like
Perfect.
reset, but also not really. So I will answer this, but let me first hear the second question, because maybe that's more local.
Yeah. A second question is actually maybe easy. The question is only if the immutable state is the end state, or can there be a loading from SSD that is immutable and will be converted back to mutable?
No. Immutable is the end state. After we've sorted things,
It's done, right? And
uh,
it's then only compacted and merged. That's the only
yeah,
thing that happens then.
yeah.
Okay.
Well, to maybe, well, there is one a representation transformation that is happening still. So both this red rectangle and this green rectangle are logically sorted array, but physically they are represented differently. So this thing here is literally an in-memory contiguous array. So 500,000 of accounts, like one by one, one by one. The table actually is a hierarchical structure. So if we zoom in into the table, the way it works is there is the index block, and this is already on disk data structure. So let's no. Let's call this somewhere. This is no. I don't want to attach anything. I want to say this is disk, which we've actually already did here. Never mind. Okay, so there is like index block, and then there is a bunch of value blocks. 1, 2, 3. Oh, okay, it's fine. And index block points to value blocks. So each block is, if I remember correctly, it's 0.5 megs in size. So this red thing is 64 megs. And when we write it out to disk, we slice it into chunks of half a meg each, and we write individual chunks to disks, and then we write an index block, which is an index into this chunk. So index block contains a sorted array of pointers to value blocks, and a parallel sorted array of minimum values in the value block. So when you look up something in an LSM table, you do a binary search in the index block, which identifies you the value block where the value belongs to, and then you binary search the value block. And then, yes, once this table gets to disk, there is also a separate process of compaction, which periodically reads a couple of tables from disk, merges them, and writes the results back in. But I think right now compaction isn't actually the bottleneck. Well, sort of like this whole thing I'm describing, it is like also part of the compaction, because compaction is about moving data from like the hoard L1 CPU cache to in-memory hash map to in-memory immutable table to level 0, and like down the LSM levels. So like compaction is the journey through the memory hierarchy. From L0 to like all the way to some kind of like S3 object storage. But at least in the TigerBeetle right now, the bottleneck, our like the reason why TigerBeetle is slow is kind of like in this part. This part is working sufficiently fast, and well, one reason for that is that like this thing is like simply not on the hot path. So this is just like some immutable data structures which can be like updated in the background, which can be like paced arbitrarily. These things here are like more mutable, so you have to update them on the main loop, and that adds up to latency. Okay. This hopefully answers the question of like other like any further transformation after we get table immutable. So kind of like not really, but a little bit. there is this slicing of array into blocks, and then there is like compaction. So the question, first question, is this hash map reset periodically? And here, yeah, I should kind of like zoom a little bit and explain why we use a hash map here. And the thinking is this. So imagine you are writing TigerBeetle and you want to like write a prototype. So you don't want to care about consensus. You don't want to care about persistence even. You just want to have like an kind of understanding of like what is the light speed, what is the fastest way to do transactions, and probably what you will do is that you'll just have an in-memory hash map, and you realize that hey, your like to process a transfer, you need two hash map lookups. So you look up credit account, you look up debit account, you update values in place, and you're done. That's it. So then, uh, once you add persistence and once you add consensus, your goal is to get as close to this two hash map lookup ideal as possible. And the main trick which allows you to do this is this assumption of locality. So in financial transactions specifically, it is true that relatively few accounts are hot. So like, you might have a billion accounts in your database, but only 1,000 of those accounts are actually accounts which are transacted against every second. So the idea here is that if you keep those 1,000 hot accounts in memory, then you could run with performance which approaches just an in-memory hash map. And then like your persistent thingy is kind of like a backup process which exists to make sure that data survives if your database crashes, but isn't otherwise on the hot path. So that's kind of like philosophy. Now, how this actually works. This, and here we'll probably start going to the code. So okay, now let's start from the forest. Okay, so the data structure like in the source code, which like contains the picture I've drawn so far, is called a forest. It's kind of like, it's not the picture itself, but it's kind of like the root of a picture. So it contains everything else. And the forest is a bunch of groves. So let me explain this way. We have two objects, transfers and accounts. As I explained, each transfer and each account actually corresponds to several LSM tree on disks. So all the trees for account are grouped in a so-called account grove. So if you look at the state machine, account this, we'll see this account grove thing. And that thing internally will contain, through pretty horrible comp-time magic, a bunch of individual LSM trees for accounts. So you see, like this is where we collect all the trees, and those groves will be grouped in the forest. So yeah, I guess what we actually want to look at is the grove, and the grove has this object. Well, it should be the grove. Where is the cache map? Okay, we have objects cache, and where is it used? Okay, yeah. So this is the thing. This is that in-memory hash map. And this data structure plays two roles. One role I kind of like described already, and that is to be the cache of individual accounts. So if we have an account and an account is hot, it's like, source of truth might be somewhere very deep in the LSM tree on disk. But we also expect this account to be mirrored in this in-memory object cache. So if we need to do something with an account, we don't actually have to go to disk. We could fetch it from the object cache. But there is also a second role which object cache plays. And this means that we need to, and okay, here I'm starting to jumping around. Sorry about that, but well, that's the way it is. And here we need to look at our prepare and prefetch methods of a state machine. So, okay, let's get back to the basics. Our task is to run transactions. Running transaction, running transfer means fetching two account balances, updating this, and saving the results. And we have 8,000 transfers in a single batch. Naive way to implement this is that you go read one transfer from disk, then you go read another transfer from disk, then you update those results, then you write the results to disk, and then you go to the next transfer. So for each transfer, you do two I/O operations. You actually can do those two I/O operations in parallel. You could concurrently look up both the transfers from disk, but between the transfers, well, you just run them sequentially. Obviously, that is kind of like not a great way to do this. So what we do instead is that we look at this entire batch of 8,000 transfers holistically. And we don't actually know whether all the transfers will succeed or fail. Maybe some transfers are just syntactically invalid and they will fail and we won't even have to run them. But the common case, the expected case, is that like most of the transfers will succeed. So what we'll do is that we'll in parallel load all the 16K accounts which might be relevant for those transfers. And this is what our prefetch operation in the state machine does. So prefetch is a synchronous operation. It accepts a callback. And the job of fetch is to load in parallel all the data which might be required to process given transfers into this in-memory cache map data structure, into the objects cache. And now, when we go to the execute operation is actually synchronous. Execute operation doesn't do any I/O, because as a precondition for execution operation is that everything is already in the object's cache. So if we look at this create transfer, so we take transfer and like, how do we actually do account lookups? We call get account, which calls get on the groove type, which is just a synchronous. Well, no, it's the wrong get. Okay, yeah, this one, which is just a synchronous lookup in that head map. So this is kind of like what makes this cache map peculiar. Because on the one hand, we want it to be the cache. We want to say our cache map stores like 1 million of accounts. And if you need to work with like 2 million of accounts, then we will evict the 1 million less recently used accounts. We just forget it. On the other hand, this cache map needs to provide a guarantee that if you prefetched an account, then the prefetched account will still be in the cache map by the time you get to execute. So inside this object cache, let me see. We'll see that. Okay, no, it's I am lost. Cache map type. Okay, yeah. Inside this cache map type, we see that we actually store two things, two data structures. One is a cache, which is a set associative cache type, and it is like, it's a bona fide cache. You can put items there, you can get items out of it, but it doesn't guarantee you that whatever you put there is going to stay put. It actually could evict arbitrary things. And then on top of this cache, there is a map data structure, which is a hash map. And the way this works is that, okay, so let's say you run in prefetch, and during prefetch, you loaded your data, you realize that, hey, the data actually isn't cached already, so you need to load it from disk. So you went to your LSM3, you did some amount of IO, you get your value, and then you're calling insert, and then you're calling upsert method on this object cache. So what happens here is that we first go and we insert our value into our cache. And that might evict some value. And because the cache map maintains this invariant that for a single batch, everything must keep in memory, we cannot just drop this value on the floor. Because it could be that the value which we are evicting right now is a value which we have just prefetched. So if this happens, rather than just dropping value on the floor, we go and insert it into our map, which is called the stash. So yeah, and that's why kind of like the data structure is called cache with a stash, which is inspired by some cuckoo hashing-like scheme where you have like a hash map, but you also have like an overflow stash, which captures values which got evicted from the hash. And the idea here is, yes, you add items to the cache, and some items might get evicted, but the items end up in a stash. So they aren't actually fully evicted. They are still there. And the kind of like maybe idea here, well, why don't you keep like everything in a stash? Well, the thing is that the stash is actually small, because once we actually executed a bunch of transactions, so we run prefetch for 8,000 transfers, then everything is in a map, which means that some things are in cache and some things are in a stash. Then we run the execute. And after this point, we actually no longer need our stash. So at this point, we actually can go and we can clear the stash. In the code, this is called compact. And compact for an object cache is indeed just like clearing the stash. So this is the answer to the question, like when do we clear this hash map? And the answer is like the hash map itself, like we never clear. It is like just an LRU cache which stores recently, well, it's not literally LRU, it's like rather like clock algorithm, but anyway, it is a cache which stores recently accessed accounts. But there is an extra stash behind this cache which catches all accounts that got evicted. And that stash we clear out once we finish prepare. And this answers a question also a light here. So I'm curious, Tobi, do you see where I have light?
I actually have another question, but no, I have not. Let me think about this.
You could ask the second question first. So it's like you can concurrently think and listen to an answer to your second question, which should make
yeah. So I
easier.
think One question, or actually, I have two questions. One question is, if you clear the hash map or the part of the hash map, then you still don't need to do IOs for the hot accounts that you have missed, right? Because you have the grid cache also. So not everything that you evict necessarily enforces a new IOP. Is that true? Or
Yes, this is true. Because so this like caches individual accounts. So this is like cache on the level of domain objects. Uh, Here in the LSM tree, we actually have another thing which is called grid cache. And grid cache is kind of like type oblivious cache, which caches the raw blocks on disk. And the relationship here is this. So grid cache caches disk blocks. It cannot actually cache an individual account. If account in grid cache, that means that a value block containing this account is in a grid cache. And that means that all accounts from these value blocks are already in the grid cache. While this in-memory cache can cache individual accounts. So like, if you have like 1 million accounts and they are next to each other in the LSM tree, so their IDs are their timestamps are sequential, then yes, the contents of grid cache and in-memory cache will be equivalent. If it is not the case, if you have 1 million accounts, but they are spread out across your LSM tree, such that each account, like for each value block, there is like at most one account of that 1 million hot set, then your in-memory object cache will contain all of those, but grid cache will contain only some, because like the cost of caching individual account in grid cache in the worst case is pretty high.
okay, cool. I think I have two more questions actually. So in this batch of transfers,
Yeah.
can there be a scan in between? Because you support scans, right?
Right. Yes. So
And this hash map is not really well suited for.
yes. This is the core of the thing. So to for people not like super familiar with TigerBeetle, there's like actually two different kinds of workloads. There are write workloads where TigerBeetle ingests new transfers and it needs to process the transfers using double entry counter logic. And this is a primary workload, something we are optimizing for. TigerBeetle also supports queries. Operations like, hey, given this account, return me all the transfers which belong to this account. The two fundamental differences between, well, there are like several differences why workflow. One is simple, one is write, and another is read. The second difference is that one is a hash map lookup. When you process transfers, you need to do only point lookups in a hash map. When you do queries, when you are looking up all transfers belonging to an account, you need to do a so-called scan. You need to do like a binary search in your sorted set of transfers, which returns like a slice, because like there are like many transfers for a given account. So there is like this like sorting thing going on. And the third reason is third difference is that TigerBeetle is deliberately optimized for write workloads. So we support reads, but we don't care all that much that reads are fast. We kind of like want to make transfers as fast as possible and kind of like be able to handle reads somewhere. And I guess I will explain how we handle reads today, and I will explain how we actually want to move the reads, move the costs imposed by reads of the fast path, which is currently imposed on like write operations. Which is again like you continue to ask the questions which are like running just a little bit ahead, which is actually good. You are prefetching. You are running prefetch for what we're talking about. But before that, let me get back to the lie which I've told you. And the lie was that. The lie was that we clear the stash once we process a single batch. This is actually not true. We clear the stash uh, once we reach this point. So once we processed a whole bar of transfers. And that means that the size of the stash is actually enough to store 500,000 of accounts, because that is worst case, where like every single transfer touches to accounts which are evicted from the cache. Why is this the case? Well, uh, this is because you also need to support lookups. So again, imagine there is like incoming transfer, and it transfers money from Bob. So you go and you look Bob in this cache, and Bob is uncached. So Bob is not the cache. You need to look up Bob in where it is actually stored. Well, the thing is, at the moment, Bob is stored in this table mutable, which is unsorted array. So you could be looking for Bob in this table immutable, but that would be a linear search through an assorted array, which is pretty slow. And we really want this to be a point lookup. So we actually want to guarantee, let's be more specific. So if Bob is here, then it is pretty sad because this array is unsorted, so this is going to be a linear lookup. If Bob is here, then this is fine because, well, this is already sorted, so we'll do like a log n binary search there. So we want to avoid this case. And to avoid this case, we actually add an extra invariant here, is that not only data for a single prefetch is in the cache map, but actually the data for the entire bar should be in the cache map. So that if you look Bob in this cache and you realize that Bob is neither in the cache nor in the stash, then you are guaranteed that it is not in table immutable. And you need to go through mutable things. So yeah, that's why we accumulate stash for the entire bar and then clear the stash at the end of the bar. And that actually, brings us to like that bottleneck and what we've been discussing about, like using a B tree, using some sorted data structure. Because this is kind of like um, the pain point, that this thing here is not maintained in a sorted order, and lookups there are slow. So we duplicate data into in-memory cache to keep lookups fast. But we also have scans. So what if instead transfer like $100 from Bob to Marina, the actual request you get is, hey, give me all transfers against Bob's accounts. This is painful because this requires sorted lookups, ordered lookups, and this cache map, although it holds all the data, it doesn't actually support sorted access. And this thing is unsorted. And here we do something super simple. Something super simple and something stupid. If a lookup comes in, we just sort in place. And this is like totally quadratic in the worst case. This is like it is quadratic in the worst case, but the worst case here is 32, because we won't be sorting for each individual lookup operation. We would be sorting for each individual batch, but still kind of like not great. And our idea here is, yeah, sure.
Yeah, I mean, yeah, exactly. So maybe that's our idea also, because I had this idea yesterday also that we maybe can do a B tree there, right? That basically splits the sorting or incrementally disperses the sorting around every insert. And that would allow us also to reduce the size of the cache map, because then we have a sorted access on the table mutable, which then would allow us to have the cache map much easier in the cache, like in the CPU cache, right? Because then we can basically, we don't need to maintain it for the whole bar, but we can actually clear it after every batch. and make it super small and tiny. And then the super hot keys, they will be very, very cache friendly. And if we need something from another batch, then we can go in the B tree and then find it there pretty easily. And the worst case space is just basically 2x because of 50% fill degree. And this is 64 megabyte. We can fix the fill degree higher, than we have a bit less worst case. But I think it's not too bad a trade-off, at least from my perspective. And that would
Yeah,
remove this max percentile and the 99 percentile that we see now. That is, I think, 4 times
yeah,
higher compared to the median.
yeah. This is certainly like this is certainly a reasonable optimization. And honestly, I kind of like not fully understand why we haven't tried a B tree yet. Maybe replacing this data structure with a B tree would kind of like would be a major win. But I want to,
I
uh,
think also, let me quickly add something,
yeah.
maybe 1 second, because I think I'm not sure if we end on time just to get the question in.
Oh, we have time.
Because
Like
the
we have time. There is no
okay,
time
okay,
limit here.
because the hard part in the B tree to implement is the merge and the deletion. But we don't need this here, right? Because the LSM tree is basically just appending, and basically deletions or changes are just new inserts, which is pretty nice. So we actually have a really hard worst case bound, even if we cheat in the merge, because we don't need the merge. Actually, we don't need to implement anything of that. So I think the code is actually not too complex, even if we were. I think we prototyped it today, just a static kind of allocation array that we can then swap out. And I think this works pretty nicely.
Yes. It is pretty likely that like B-tree is a better data structure for table immutable. It is very reasonable hypothesis. Again, like important context. Like TigerBeetle has very right high level design, so we are pretty confident that like our high level design can like unlock infinite performance. But in this like nitty gritty details like specific data structure choices, it is like basically like we used what we've already had written. We already had like sort algorithm from the Zig standard library, but we didn't have a B tree. So let's just use sort. Although I kind of like my gut feeling is that maybe B3 is not the right answer here. Maybe we could do slightly better there. And here, like we really start digging into like what is like the theoretically best possible performance here. So and for that, I want to slightly quantify for how I think B3 would affect our performance here. So it is true that B-tree should be able to reduce our memory usage, because with a B-tree here, then we indeed would be able to flash the stash part of a cache map after every request, which cuts the stash size by 32, which is actually pretty sizable. But I don't think that in and of itself that would affect performance, because in the cache map, well, actually, let's go to the grove and let's uh, go to prefetch enqueue path. So prefetch enqueue is that thing which like kind of like the cost path on the like right. So this is where writes um, spend most time. And the hypothesis here is that most of the data should be in the object cache. So uh, probability of stuff being out, like if you have a lot of things outside of object cache, that means that you need like bigger object cache. Ideally, your entire working set should be in main memory, because it shouldn't be like that many accounts. And here, when we go into our cache map, we first look up from the cache and then we look up from the stash. And again, stash only holds stuff which got evicted. So stash contains things which are unlikely to get evicted. And actually, like we expect that we all need a single uh, cache map lookup here for processing a single transfer, which is going to be just a single lookup in the cache map, which is going to be a hit. So yes, we do make stash smaller if we use B-tree, and that improves our memory usage. But I don't think that in and of itself improves our um, performance, because it is like
Yeah.
we still expect like on average one hash map lookup, and
I think this is
this
fair
is
enough. The main thing with the incremental sorting index is basically first to reduce the spike of the latency that we see. That's
yeah
basically the
yeah
first thing I wanted to look at. That was just
yeah
a random
yeah
thought. Yeah, but I mean,
yeah
fair enough. That's true.
yeah
Whoa.
yeah.
Is
That's
this loud now?
a little
Can
bit,
you hear the
but I
coffee
think
machine doing things? No, no, it's done.
a little bit.
Good.
It's fine. Uh, okay. So, and this is actually I think something which bugs me, because like I've said that hey we only need like two hash map lookups. Like the thing is like right now we do 4, because this thing here during prefetch is a cache map lookup. So if we go to the state machine and we go into prefetch, create transfers, uh, yeah. So prefetch debit account, prefetch debit account. So this thing here like does a cache map lookup. But when if you go to the execute, create, this is called create transfer. And we do get account here, and here we do group accounts get. This is also a hash map lookup, because due to like the way our cache map and stack works, actually like between your prefetch and between execute, your account might get moved from the cache map to the stash. So you cannot just like remember the pointer there, and you need the second hash map lookup. So this is like potentially like also something to optimize. But this is not the bottleneck. The bottleneck, like right now, is exactly what you were saying, that like sorting is slow. And let me zoom a little bit, just a little bit into the sorting, because there's another lie I've told you, and I've told you that like table immutable is unsorted. That's not true. Table immutable, well, as of recently, this is like really recent optimization, like this month or about that. It is partially sorted. Specifically, uh, whenever we process a batch, we append like a little bit to the uh, to the end of the immutable table. And after we appended a single batch, we sort this batch. So in reality, our table immutable is 32 chunks, and each individual chunk is sorted. And in this like final sort, we don't have to sort everything. We only need to sort chunks against each other. So kind of like perhaps the optimal algorithm here would be to run a 32-way merge based on the heap with size 32, but you actually just call standard library sort routine, because internally it already takes good advantage of things being partially sorted. And that actually brings us to what I wanted to kind of like discuss. The big idea is like, why do we need sorting at all? And it sort of true that we like only need data to be sorted. We need data to be sorted for two reasons. One is that if data is uncached, if data is not in the cache, we need to look up, and we need to look it up in a sorted data structure, because that's how our LSM tree works. The second reason why we need sorting is that we do queries. So queries need access to sorted data. There is no way around it. You need to sort something. But the queries are cold path. We don't we don't care if queries are slow. We only care, again, we query if queries are slow, but much less than if the transfers are slow. So what we actually are thinking is that we'll do like something like super horrible when a query comes in. So you see, if there is a query,
Basically, you move it, right?
We want, okay, so it's embarrassing. I thought this is a laser, but it's not a laser. It's actually a marker. Okay. God praise and do. So the idea here is that if you see a batch which is query, then you kind of like say, okay, this entire 32 batch thing ends here. So as long as you have a query, you immediately move from this place to this place. You just don't have like table immutable at all. You kind of like pulls fake operations, and you say, okay, so now we have stuff in memory, and we execute queries over that. And there's like two motivations there. One motivation is like performance, like we just don't want to handle this case. We don't worry about making queries slower if that allows us to not maintain sortedness on the insert path. The second motivation is queries can return arbitrary results. But in TigerBeetle, everything has finite size. So, there is only like 1 megabyte for results of a query in a message. And if your query returns large data set, then you need to paginate it somewhere, some way. But to have pagination, you need to be able to provide some consistency guarantee across the queries. Because, if you just do pagination stupidly, then the first page and the second page might actually contain contradictory results, because there might be some transfers in between. So we need to query against a particular snapshot. And we only want to allow creating snapshots at these bar boundaries, kind of like for simplicity. So that's kind of like the long-term path for queries. Whenever you do a query, you implicitly acquire a snapshot at the nearest bar, and then you run the query against um, you run the query against that snapshot. So ideally, we shouldn't be maintaining this sort of thing. And this brings me to that, what I was saying, that hey, like B-tree sounds like an obvious thing we should definitely try. The reason why we didn't try this is because, well, there is like only so many things we need to to try, and to be honest, we haven't got to like optimizing performance at all at this point. But if you think about this situation where like queries only see this part, so queries never see this, then it sort of feels like sorting should be more efficient than B-tree, because constructing B-tree incrementally is just more work than doing a sort. And okay, the problem with sorting is that it is concentrated in time. So sorting blows up your latency, but potentially you could mask that by moving sorting to the background. Again, you could maintain this invariant, like you could extend this invariant and say, okay, so let's say that the stash now covers 2 bars worth of things. So when you are here, what you do is that you sort this entire thing, but you sort this in the background. you sort this on the background thread. So you cannot, you obviously cannot access it in this case. But it doesn't matter because you don't need to access it because all the data is still in the stash. And then, like, it gets sorted and then it gets into compaction. And this honestly sort of feels like uh, speed of light performance here. So if we zoom at individual transfer, what happens here, like in the speed of light scenario? Well, you go and you do a hash map lookup for account, and that hash map lookup is cached. So like one hash map account, and you get a pointer to an account object out of this hash map lookup. Then you do a second hash map lookup for a second account, and you also get a pointer to an account, and those pointers are stable. And that isn't the fish. Then you get to the execute. In the execute, you have those two pointers still, they are stable. You go and you update the balances, and you are done. Then at the end of the bar, you take all the balances which were updated within this bar, and you sort them. You produce this single sorted array, but this all happens in the background of the main thread. And then you like get this after one more bar, you get this in-memory sorted array, which you start compacting to disk. And we are not here yet. One thing is that we don't have this background sorting. So this sort over here is a big bubble in our latency. Then we kind of like do redundant work here because like these incremental sorts, they help latency, but they sort of increase the overall workload we do. So ideally, we actually don't do incremental sort here and do just one non-incremental, but parallel and background sort here. And yeah, there is also this thing where we have 4 hash map lookups because we don't have pointer stability. But perhaps this is just too hypothetical. Perhaps we should just make this thing a B tree, and then if it is a B tree, then it could actually remain B tree all the way through here, and gets converted immediately to LSM tree. Maybe this doesn't have to be a B tree. Maybe this needs to be an in-memory LSM tree, which would also be fine. At some point, I even convinced myself that this has to be, or at least could be, beneficially a skip list. But I don't.
Mm.
Well, okay. I remember. Mm, I remember why I think this might be good as a skip list. The thing here is that you don't have to update this thing after every individual transfer. You actually could update it like in batch after like 8,000 transfers. So ideally, we want a data structure here which supports like bulk insert, where like you just insert like many things in a row. And skip lists feel kind of like a nice for this bulk insert, because what you could do is that you could insert a middle item in the skip list, and then you realize that, hey, everything that's to the left of your middle item goes to the left, everything to the right of your item goes to the right. So you could actually run this in parallel again. But actually, maybe that works with B tree as well. Yeah, it's okay. Yeah, skip list is not needed because the same thing works with B tree. I think you could like insert in the middle of a tree and then insert to the left and right parts separately and concurrently. Or maybe not. Okay, so I think, Tobi, that is mostly all I know about the right path.
Yeah,
Curious
that
about any
sounds
questions.
pretty good. I think I covered everything during the stream. I think I would start just with the B tree, just because, I mean, it's easy to implement for me. I've done this multiple times. and to learn about like how it will affect latency. And then we can think about this background sorting. But I think there must be more things in place, right? For instance, the background sorter itself, and also the like moving read queries to the sparse boundaries and these kind of things. So maybe the first thing is just to implement quickly the speed tree to see if it flattens the latency spikes, and then we can think about this background sorting more.
Yeah. And also, I would maybe like do like two approaches here. One is like incrementally optimize what we have here, but I really think that it would be a good idea to think from the first principles. What is the speed of light? Like
Yeah.
forget about TigerBeetle as it exists. Like start with a blank slate, and like what would be like the fastest possible operation? Could it be like just like two hash map lookups, like we had in this like experiment with just like in memory hash table without persistence, and like then um, think about like maybe there is like maybe we need to throw everything away here and like start from scratch because maybe there is like first principles uh, completely different data structure. But B-tree definitely is a good first try just to see how it works because I bet I bet it will reduce our tail latency pretty significantly. The question is, would it be a local optimum or not?
Probably not. I think it's just the first step to see to fix the tail latency problem for now, and then we cover. Then we need to address throughput, right? This only covers basically the tail latency problem, but it will
Yeah,
not like increase throughput so much, or probably not at
yeah,
all.
yeah. I think well, my theory is that it should like decrease throughput a bit, but well, who knows?
Yeah, a bit.
Uh,
Yeah.
okay. And there is an excellent question in the chat. Is that can you explain again why sorting introduces tail latency if it is done in the background? I cannot explain it again because I don't think I've explained it at all. So let's make it clear. Right now, sorting is not in the background. Right now, sorting is in foreground. So this arrow actually blocks the main event loop. And while we are sorting this thing, well, nothing else happens. And it is pretty clear why this displays tail latency, because it's just the working set is too high. Like, you need to sort like 16 megs of data. Like CPUs are fast, but like 16 megs, it's still like, it's enormous amount of data. So it takes some milliseconds to sort this out. And the reason why this sort is a foreground is that we want to atomically uh, switch here. So like uh, moved from this batch to this batch, we already need some way to do lookups in our like in-memory table. Because if we just let the sort run in the background, and then turns out that we need to look up data which is stored in the array which we are currently sorting, then we are kind of like out of luck, because if we try to look up it, we'll get like data races and all that stuff. Again, the sort would be made in the background if we extend our cache map to cover 2 bars, but that's also kind of like a hard sell because it increases memory usage pretty substantially. And then we'll need to have this extra code which says, hey, if we hit a query, then we'll actually block until our sorting finishes. And I guess another important consideration here is that background sorting is very theoretical because right now TigerBeetle is 100% single threaded. There is no background thread pool at all. And this is also actually intentional because like you can always make stuff faster by adding a thread pool. But we actually deliberately postponed adding thread pool for later because we want to investigate whether we could squeeze more blood out of sequential execution, where we could make it really fast. And once we realize that, hey, we can never ever make sequential execution faster, at that point we'll start parallelizing things. because if you start with parallelizing things, then it might actually be harder to then optimize the sequential execution. Or it might be the case that you optimize sequential execution and then you realize that the part which you parallelized is not actually a bottleneck at all. Because yeah, as you've seen in this episode, there is like this like question of like, do we actually need sorting here? Maybe we don't need sorting here at all if we do like some messy magic stuff with queries. Okay, so hopefully that answers the chat question. So Tobi, are you happy? Do you think that's it?
Yeah,
Do you
I'm
think
very happy.
finish? Okay, then
Pretty nice.
let's
Thank you.
yeah, sure. Then let's stop here. And as usual, uh, the next episode is going to be next Thursday at 5 p.m. UTC live on Twitch. And if you miss that next episode, or if you have already missed the current episode, which was very exciting, thanks Tobi, it is always uploaded on YouTube right after we finish. Okay, thanks for listening and goodbye.